So in this problem, we have a lifeguard, Martin, who is sitting at a lifeguard station, and he sees a swimmer in the water signaling for help. So from the description and the diagram, we can see that the swimmer is 80 feet out from the perpendicular line from the shore to the swimmer. And that line hits the beach 150 feet away from the lifeguard station. We're also told that Martin can swim at a rate of 4 feet per second and can run at 6 feet per second along the beach. So what we're asked to find is how far Martin should run from his tower down the beach before he jumps into the water and starts swimming to get to the swimmer. We want to minimize the time it takes to get to the distressed swimmer. So Martin is going to run down the beach for a distance, and then he's going to swim for a distance. And we're trying to minimize that overall total time. So let's take a look at this diagram and see what relationships we can find between the different distances involved in the process here. We know that the total horizontal distance along this lower edge is 150 feet. We want to find the point here where Martin's going to enter the water. So we have a right triangle over here. Let's give this length of the right triangle, the leg that is part of that horizontal distance, variable name x, and then we can also mark that the distance from the lifeguard tower to the point where Martin gets in the water is 150 minus x. With that, we can also see that this distance, the distance that Martin is going to swim, that is the hypotenuse of that right triangle. And so we can label that distance as the square root of x squared plus 80 squared. That's just using the Pythagorean theorem. So these expressions represent distances in this problem, but what we want to minimize here is time. So we need to have a relationship between distance and time. So we know that the relationship between distance and time is given by the formula distance equals rate times time. And remember that we also have the rates. We have both the swim rate and the run rate. So since we're trying to minimize times, we want to put times in terms of distance and rate. So we can solve this equation for time, and we get time equals distance divided by rate. So again, the hypotenuse of the triangle, that is the distance that Martin's going to swim, and the length along the beach, that is the distance that Martin's going to run. We also know Martin's rate at which he runs is 6 feet per second, and we know that Martin's rate at which he swims is 4 feet per second. So with that, we can piece together the time that it's going to take Martin to swim is the distance that he's going to swim divided by the swim rate. And the time it's going to take Martin to run will be the distance that he's going to run divided by his run rate. So we have everything now that we need to write our objective function. Remember, our objective here is to minimize time. So we want a function that gives us the total time. And the total time is going to be the time that he's going to swim plus the time that he's going to run. So now we have an expression for the total time as a function of x. So this is my objective function. It's the total swim time, which we worked out up here. I just wrote it so that it's a little easier to deal with. And then the total run time. That's my objective function. So that's the function I'm going to minimize. That means I need to find the derivative. So in this first term, I'm going to apply chain rule. And in the second term, I have a constant multiple of 1/6 times the derivative of the part in the parentheses. And the derivative of 150 is 0. The derivative of negative x is -1. Now I can simplify some things a little bit. Here I have a factor of 2 and I have a factor of 1/2. So now I'm going to write this as x over 4 times the square root of x squared plus 80 squared minus 1/6. That's my derivative function. I want to find critical numbers, so I'm going to set this equal to 0. To solve this, I'll take the 1/6 to the other side of the equal sign. At this point, we'll probably just want to cross multiply. Now I have an equation that has a square root expression on one side, and my variable x is inside that square root. So I'm going to square both sides of the equation in order to get rid of the square root. And after distributing the 16 through on the right-hand side, now I can subtract the 16x squared and then divide both sides by 20. And at this point, we would use a calculator to evaluate this, and we get that x squared equals 5,120. And so to find x, we're going to take the square root. We don't need the negative square root solution because in the context of this problem, negative result doesn't make any sense, but we get 71.554 and some change. So that's our value of x. Now, let's go back and look at our diagram, because what we want to find is how far should Martin run from his tower down the beach before entering the water and swimming the rest of the way. So that's this distance. That's the distance we're asked to find in the first part of the question. Since what we found is x, the answer that we want in this first part of the question is 150 minus x. And so we have 150 minus 71.6, and that gives us 78.4 feet as our answer for the first part. The second part of the question asks, what is the total time that it takes Martin to reach the distressed swimmer, rounded to 1 decimal place? So let's go all the way back to the objective function that we found for t in terms of x. So at this point, I would just use Desmos, or you could use your hand calculator. But it'll be a little bit easier with Desmos. So I computed the value. I evaluated the square root of 5140 to have the value of our critical number. This was the x that was our critical number. Remember, that's that base of the right triangle. And then I can just enter the expression for the objective function. That's the function for the total time that we came up with at the beginning of the problem. And then that makes it very easy to evaluate that function at our critical number, which gives us the total time when the total time is minimized. So we have 39.9 seconds. And again, that's total time at our critical number, approximately 71.6. But notice that by doing it in the calculator, I avoided any rounding error.